Optimizing emergency power supply in today's high-stakes digital landscape is no longer a matter of simple backup, but a sophisticated ballet of predictive intelligence, dynamic response, and precision engineering. This necessitates a fundamental shift in our approach, moving beyond outdated paradigms and embracing a more resilient blueprint for 2026 and beyond. Our ultimate goal is to ensure uninterrupted operation and data integrity, even in the face of increasingly complex and unforeseen challenges. Safeguarding critical infrastructure against any power disruption. Let's delve into the redundancy paradox, which highlights a critical flaw in traditional approaches to emergency power. The ubiquitous N1 configuration, for decades considered the gold standard for achieving reliability, frequently buckles under the immense thermal stress generated by modern, AI-driven high-density racks. This isn't merely a matter of having an extra unit, it's about the ability of that redundant unit to perform effectively and reliably when ambient temperatures within a data center soar, potentially causing thermal throttling or even outright failure. Therefore, a simple, static hardware backup is proving to be increasingly insufficient. We must fundamentally shift our focus to implementing active-active synchronization across redundant, uninterruptible power supply UPS arrays. This advanced configuration ensures that all components within the redundant system are not just passively standing by, but are actively participating in sharing the electrical load, maintaining continuous operation. This means they are constantly online and ready to seamlessly take over the full load without any discernible interruption or hiccup, significantly enhancing system stability. Furthermore, it is absolutely imperative that we meticulously identify and mitigate hidden single points of failure, particularly those residing within static transfer switches. These seemingly innocuous components, if not properly designed, monitored, and maintained, possess the potential to compromise the integrity of the entire emergency power chain, effectively transforming what was intended to be a robust, redundant system into a house of cards, susceptible to a single, critical point of collapse. Consequently, thorough auditing, rigorous testing, and continuous real-time monitoring of these transfer switches are paramount to ensuring overall system resilience. Moving forward, predictive intelligence and battery health represent the next, essential frontier in emergency power optimization. We must evolve beyond the outdated practice of scheduled voltage tests, which offer only a fleeting snapshot in time and can miss critical degradation between test cycles. Instead, we need to implement 247 real-time internal impedance monitoring for every single cell within our extensive battery banks. This granular level of data collection provides truly invaluable insights into the precise health and performance of each individual cell. With this wealth of information, sophisticated, AI-driven analytics can then be deployed effectively to predict chemical degradation and the potential for thermal runaway long before any actual failure occurs. Imagine the transformative power of knowing with high certainty that a specific battery cell is nearing its end of life, or exhibiting subtle but critical signs of impending thermal issues. This capability allows for highly proactive intervention, enabling preventative maintenance and replacement, thereby circumventing potentially catastrophic failures and unplanned downtime. Crucially, this comprehensive battery health data must be seamlessly and intelligently integrated into the primary power management dashboard. This integration is vital as it completely eliminates the dangerous assumption of zombie capacity, where a battery might appear superficially functional during routine checks, but actually lacks the true charge holding capability or discharge performance required during an actual power event. This can lead to unexpected outages during the most critical times, making real-time, integrated data indispensable. Dynamic load shedding strategies are absolutely essential for maintaining operational continuity and preserving critical functionality during periods of grid instability or a full power outage. This involves intelligently automating the prioritization of mission-critical workloads over non-essential background processes. During a power event, the system should be designed to intelligently and instantaneously shed non-critical loads, ensuring that the most vital operations remain online and functional for as long as possible. More aggressively and with even greater precision, we need to implement microsecond response protocols that specifically shed heat generating non-critical hardware. This is not solely about conserving electrical power. It is equally, if not more, about preserving the cooling budget. A frequently overlooked, but profoundly critical aspect in emergency scenarios, particularly with the proliferation of high-density computing environments. By strategically reducing heat output from non-essential hardware, we significantly extend the operational longevity of the remaining critical infrastructure, preventing thermal shutdowns. This sophisticated approach effectively bridges the often significant gap between theoretical battery runtime calculations and actual operational longevity, especially in catastrophic collapse scenarios where every single watt of power and every degree of temperature rise can drastically impact system endurance. Precision maintenance in high-stakes environments is no longer an optional luxury, but an absolute necessity for achieving true resilience. Adopting standardized digital twinning technology allows us to create highly accurate virtual replicas of our power infrastructure. This enables us to meticulously simulate power failover sequences and various failure scenarios without ever risking live production environments or disrupting critical operations. This capability facilitates thorough testing, validation, and optimization of emergency protocols, helping to identify and rectify weaknesses before they ever manifest. In a real-world event, we must fundamentally transition from the outdated model of reactive repairs, which are inherently costly, disruptive, and often lead to extended downtime, to proactive precision maintenance protocols. These protocols are meticulously based on real-time hardware telemetry, where sensors embedded throughout the power infrastructure provide a continuous, rich stream of operational data. This data empowers us to perform predictive maintenance, meaning we can precisely replace components before they actually fail, optimize their performance, and drastically minimize unscheduled downtime. Furthermore, ensuring seamless transition timing is unequivocally critical. This requires meticulous auditing of the synchronization, frequency, and phase between independent power modules. Any drift or discrepancy in synchronization, even a tiny one, can lead to glitches, power dips, or even complete outages during a power transfer, thereby undermining the entire redundancy effort and compromising system stability. The Resilience Blueprint for 2026 mandates a truly unified and intelligent ecosystem for emergency power. All components, from the individual UPS units to the static transfer switches, the generators, and even the cooling systems, must be tightly synchronized and seamlessly integrated to prioritize data integrity above mere system uptime. An infrastructure that is technically up, but whose data is compromised or corrupted, is, by definition, not truly resilient. We must also proactively evaluate the profound impact of emerging technologies, such as advanced liquid cooling solutions and the increasing deployment of edge computing, on traditional emergency power distribution models. These innovations introduce both new challenges and exciting opportunities for optimized power management. Finally, establishing a robust and continuous improvement loop is absolutely vital. Automated post-mortem data analysis from every single power event, whether it's a simulated drill or a real-world incident, must be systematically captured and thoroughly analyzed. This invaluable data should then inform and guide the next generation of infrastructure scaling, design refinements, and operational protocols. This iterative process of learning, adapting, and continuously improving ensures that our emergency power systems are not static, but are dynamic, intelligent, and constantly evolving to meet the complex and ever-changing demands of the modern technological landscape, guaranteeing superior resilience and unwavering reliability.